who came up with this crazy idea that black holes could create new universes?
Well, the first person to say that black holes might be, giving birth to universes was John Wheeler, the American physicist John Wheeler, back in the 70s, I think. And he's pretty much the guy who probably invented the term black hole. So this is very early, although it's disputed whether he invented the term black hole or a heckler at one of his talks invented it, because he kept calling them completely gravitationally collapsed objects. And people say, that's 13 syllables, you need something shorter. So black holes. He realized we had these two problems. Like one is, and they both involve singularities. One is black holes where you've got mass energy collapsing to a point and disappearing from the universe. And the other is the Big Bang, where mass energy appears from a point and expands to form a universe. And he was the first person, I think, to say, let's put these two things together because they look awfully like exactly the same thing seen from different sides, which I think is a massively underexplored, speculative idea. And then one of, not quite a student, but a guy who's mentored a little bit by him, Lee Smolin, another theoretical physicist, about 20 years later, is reading a bunch of evolutionary biology. And he, just for fun, because you need a break from loop quantum gravity, which was his thing. And he realized that if a parent universe with mass energy collapsing to a point in a black hole and bouncing to form a Big Bang with mass energy expanding to form a new universe, in that transition, if there was a slight variation in the basic parameters of matter, if there was a slight variation in things like the weak and nuclear force, strong nuclear force, electromagnetism, whatever, any of the the mass of any of the particles, if they varied slightly, not randomly but slightly, you'd get inheritance. That you'd get and you'd get Darwinian evolution, because the slight variation would be inherited. It would lead to either more or less black hole production, which would mean more or less offspring, more or less child universes, and therefore that variation would, if it was a successful one, led to more reproductive success, would be passed on more often. And so you should over time get a kind of runaway reproductive success of universes, because you get more and more of the offspring that had the basic parameters of matter that led to more and more black holes. You get a branching tree of universes where it moves strongly towards black hole production. And that was Lee Smolin's idea back in the 90s, early 90s. And really, I think it's maybe the biggest unexplored idea in any of the sciences. I think it's the most fruitful and interesting idea that has not really been properly explored. I mean, a small number of people have played around with it over the years, but as far as I know, I think at the moment I'm probably the only person on Earth who's been paid to study this time. And that seems to me crazy because it's such a generative idea. And I've been using it to make predictions about the early universe that turn out to look accurate. And it's just a very, very powerful, it's got huge explanatory force. It's got huge predictive power, I think, and yet almost nobody's been working on it. So I've been writing a book about this, and the book has turned into an actual research project where I'm actually pushing it forward, because I realized there's just almost nobody playing around with this. And I can see why. There are very strong sociological reasons why it wasn't picked up on, some of which reflect badly on science, and some of which are just intrinsic to the nature of highly siloed, highly specialized sciences. And there's no bad guys. But it has been hugely neglected. Yeah.
So can a universe come out of a black hole? Is it possible? Like, why would people not think about it? Is it, because I suppose it's like, okay, you connect two weird things together. We don't know where our universe comes from, and we don't know what happens in a black hole. So then you go, yeah. Is it just that, or is it? How does it work?
Well, you can. I mean, it's very possible to say there's no proof that this happens. We're stuck inside a single example of a universe, so it's totally speculative, and it's perfectly easy to dismiss it. And a lot of people do dismiss it, and I get it. Okay, but if you were to ask any of the people that dismiss this, so what's your better explanation for how mass energy comes into existence at a point and expands in the Big Bang? And what's your better explanation for where mass energy disappears to when it disappears from our universe to a point in a black hole? They never come up, in my experience, with a better explanation. They don't come up with any explanation. They just say, oh, well, two weird things. I don't think that's very satisfactory, and I don't think it's very scientific to say, let's dismiss the really obvious-looking solution out of hand without even thinking about it for 5 minutes and revel in our ignorance. I don't think that's very scientific. I think exploring this very thoroughly is something that science should be pretty heavily focused on, and it has not been in ways that are fascinating to me, very, very sociologically interesting. Yeah. So, it explains a heck of a lot of possible things. The reason I think Lee Smolin really liked it was it gives you a possible explanation for the fine-tuning problem. Because we do have this interesting, again, some people will say there isn't a fine-tuning problem because if maybe there's an infinite number of universes and some of them will look fine-tuned. If there's an infinite number of them, there'll have to be a few that look fine-tuned just by chance. And we will only be in a fine-tuned one because it takes a fine-tuned universe to generate complex things like life. So that the anthropic argument, the anthropic principle, that obviously we're in a complicated universe because we couldn't be here to observe it if we weren't. But that always struck me as being very like the rugby drinking song of we're here because we're here because we're here because we're here. It's not an argument. There's no explanatory mechanism here. There's just a throw an infinite number of universes at the problem and you can solve it. Well, throw an infinite number of anything at any problem, you can solve it. If you haven't really, I think you're going to be much better off with the theory that gives you a ratchet, that gives you a mechanism that will get you to this ultra complex, self-complexifying, self-ordering system through a process that we understand quite well, which is evolution. From a starting point of absolute simplicity, you don't need to start with a complicated universe. You can start with the simplest possible matter, and all it needs to do is reproduce. All it needs to do is flip, and black hole, big bang. That's all you need. No structures, no nothing, and you can get step by step to something like this over time. And I think that's really well worth exploring. And I think the people that dismiss it by saying it's speculative, we can't prove it because we can only see the inside of one universe, are actually wrong. You can actually make predictions with this. The predictions are turning out to be accurate. And you also, as well as the predictions, you can also explain a lot of otherwise rather puzzling things about our universe using an evolutionary model that you can't really explain any other way. You just have to shrug at. And I think that's the circumstantial evidence for it is quite, I think, powerful, quite interesting, and again deserves more scrutiny. Yeah.
So I suppose you'd say that if we just take this black holes and slight variations in the new universes that sort of emerge out of them, can that then explain why our universe is the way it is? Sort of like rather than going, okay, there was a big bang and it's how it was, it's how our universe is. We can kind of think, well, what is the history? Where do we come from in the lineage of different universes before us?
Well, yeah, an evolutionary history just does get you can use an evolutionary mechanism to get here in ways that are actually increasingly comprehensive. Like the original version of this theory was quite speculative. Like Lee Smolin's original version, he was doing this in the early 90s. There was only really one kind of black hole that we knew of, which was stellar collapse black holes, where a star gets to the end of its life and collapses under its own gravity because it's no longer holding itself up with radiation because it's run out of fuel. It collapses, and if it's big enough, it forms a black hole. It keeps on collapsing to a point, or to a singularity, or whatever, to a point where our theories break down because we don't really know what happens at a singularity. So, it's mathematically a singularity if you extend general relativity down through a black hole, or if you extend quantum mechanics down. Probably isn't actually an actual singularity. It's probably some Planck length weirdness that happens that we don't really understand. We have a breakdown in our theories at that point, which is also, again, very, let's say, suggestive that none of our theories operate, and we know that they don't operate at the point of maximum collapse in a black hole. So it's in a knowledge shadow. So I think anyone who dismisses this theory on the grounds that they know it can't happen is going way beyond the data. We have the singularity at the Big Bang and the singularity at the black hole whether or not they're the same thing, are the points where all our current theories break down, and we do not have a clear model of what happens there. So you can't dismiss it on the grounds that we've proved it can't happen. You actually have some open territory there to explore.
Mm.
Go on. I didn't properly answer your question there, but reformulate it and I'll go again.
No, I just find it fascinating. Like, I wonder how a universe would slightly change the fundamental parameters of physics and then go again. But it's fascinating.
We don't know the mechanism. So, like, as I have often said here, we're at the point with this theory. Biological evolution was that when Darwin published The Origin of Species, but he didn't know what the hereditary mechanism was. He worried about this. He knew this was a hole in his theory, but he felt the theory was so powerful in its explanatory force that he had to go for it. And he didn't know about genes. He didn't know about DNA. All of that stuff came, nearly a century later. That's the point we're at now. We don't know what the mechanism of inheritance is. We don't know why or how there would be a slight variation. But what we do know is if there were a slight variation, you could end up with you should end up with a universe like this. And I think ultimately we will probably find or theorize our way to a mechanism that works. I think to dismiss the theory because we don't have the mechanism of inheritance is to essentially make the mistake that people did with Darwin's Origin of Species, to dismiss DNA or biological evolution because he hadn't discovered DNA yet. This does have like predictive and explanatory power, even in the absence of a mechanism of inheritance. Yeah.
Like what? So people. Go on.
Well, I walk you through the theory as it currently is. The version I've been working on is called three-stage cosmological natural selection, and it's developed a lot from Smollen's original theory. And I think a lot of the problem here is when you talk to people about this, they vaguely remember hearing about Smollen's original theory 10 or 20 years ago, or 5 years ago if they're younger people and looked at something on YouTube. But their theory is about 20 or 30 years out of date. So the version we're working on, the version I'm working on, takes Smollen's original theory: universe is reproduced through black holes giving birth to big bangs with a slight variation in the basic parameters of matter, and the universes that generate more black holes will be more reproductively successful. So you should end up with a lot of black holes. And our universe has already generated, like, I think 40 quintillion black holes. So from the last survey they did a couple of years ago, where they worked out the maths on that, there's about 40 quintillion black holes already just from stellar collapses. But the theory was advanced by several other people in the past 20 years. But people like Clement Vidal, but like John Smart, there's a mathematician in Canvas called Louis Crane. There's Michael Price. There's various people have played around with this, all of them in their spare time, because there isn't a field for this, and they incorporated intelligence into it, because Smollen's original version doesn't really explain why there's intelligent life in our universe. How does that work for the unit of selection that is the universe? He doesn't go there. He just says, well, it's exploring this possibility space. It's getting more complex because that makes for more stellar collapse black holes, and we're a side effect. So he treats us as a side effect. But various other people realize that if you have intelligent life that can manipulate matter, that can build technologies, one of the things you can do ultimately, given a sufficiently advanced intelligence manipulating sufficiently advanced technology, is you could build small black holes. You could generate black holes that haven't been that nature itself couldn't produce just by bumping things into each other. Okay, it's technically possible. It's unbelievably technically difficult, but it's not inconceivably difficult. It's now the original versions of this theory said they had a slightly, I would say, a weak version of the argument, where they were saying it's technically possible that intelligent life could do this. So intelligent life, because it's interested in doing things, might do this. And I make a much stronger argument. I make a strong argument for intelligent life making small black holes, based on the fact that small black holes are, if you can make them, by far the most efficient and sustainable energy source in our universe. There are every life form tries to optimize its energy efficiency. From hermit crabs to amoebas to giraffes, we're all trying to use the energy that's available to us as efficiently as possible to survive and reproduce. Intelligent life forms are able to do that with external energy sources. If you're hungry, the energy you get might come from an avocado that was flown here from California, right? You're using external energy sources to give you your energy. So what do? We push that energy up the efficiency slope. Early hunter-gatherers are using their own muscle power. Then you start to use the muscle power of animals. Then you start to, you burn wood. You tap water with water wheels, and you get solar. You get wind power. You burn oil. You burn gas. You burn coal. You start to use fission power once you crack that. And then you try and crack fusion power, which we're close to. There's an endpoint to that, though, in our universe, and the endpoint is small black holes. The energy efficiency of anything chemical is extremely low. The energy you're getting from matter in fission is up to 0.1% of the mass will be turned into energy. The upper limit for fusion is about 0.7% of the mass will get turned into energy. The upper point for dropping matter into a small black hole, you can get up to 42% of the mass back as energy. So it's 60 times more efficient than even fusion, and you can use any matter at all. You're not restricted to a limited number of isotopes. So if you're able to make small black holes, you can just drop matter in, and as we see looking around the universe, all of the brightest things in our universe, all of them are basically black holes with stuff falling into them. Quasars and blazars and Seyfert galaxies, and they all turn out to be, that's matter falling into a black hole, because it craps out so much energy. And so intelligent life, if it ever did develop in a universe, if a universe just exploring the possibility space of matter blindly as happens in evolutionary models, if it stumbles on intelligent life, and intelligent life is able to manipulate matter to build small black holes, it will produce so many more black holes per unit mass that will be massively selected for. They will generate so many offspring universes, which will have that set of parameters that allowed that life to develop, that you will end up with a runaway, that branch of the evolutionary tree of universes is going to be unbelievably successful. So under that model, which is why it's vastly superior to the anthropic principle, the idea that you can throw an infinite number of universes at the problem and one of them will be complicated. Under that model, most universes will actually come from parent universes that had intelligent life, where technology was used to make small black holes. So we're very likely to be in such a universe. We're actually the dominant class of universe along our evolutionary line are ones that contain life, intelligent life and technology. I really like that. That seems to me to be much more frugal and much more scientific and conservative than any of the other multiverse models, or certainly any theory that says we can't explain the Big Bang, we can't explain black holes, we can't explain why our universe self-orders and self-complexifies. Yeah.
So in the first place, Lee Smolin is saying there's this correlation between the complexity of a universe and then more black holes, and then if for those universes that create life like us, I suppose if we could create black holes, then I see the logic. If it's possible, then we should come from a universe where people were creating black holes. One question I have is, would creating a black hole lead to the same parameters of our universe going to that? Like, I wonder if, does it matter the way a black hole is produced? And I guess these, maybe it gets into these unanswered questions of,
It's a good question.
We don't know what
Yeah.
is on the other side of a black hole.
I think it's a really good question. I think when you've got a stellar collapse black hole, it just has to essentially pass on the parameters of our universe with some slight random variation. When you're generating one, if we've advanced our technology sufficiently to that point, maybe we do have some kind of control over the parameters that are passed on. Yeah, I really don't see. I see that as a very, very open and interesting question. I feel that in the same way that we now that we've taken some kind of control over DNA reproduction, we are able to edit genes to express differently and express things in ways that nature couldn't have done. You know, we can insert fluorescent jellyfish genes into mice. We can do, and we're just at the very beginning of that process. So I think once a conscious organism is in charge of a process, it will refine that process. And I think if we are ever building out small technological black holes as power sources, and we know that we're generating a universe every time we do that, there's this kind of a huge moral imperative to not generate a horrible universe full of suffering, or what do you? I think there are moral questions there that are really, really interesting. Perhaps the moral thing to do is just produce child universes that only produce stars and don't produce life forms because you can't control the amount of suffering. Or maybe you just try to optimize for life forms because life is essentially a good thing to generate. And then you allow those life forms to explore the possibility space, make their choices, live, that becomes a phenomenally interesting moral question. So I don't know the answer to it. I do think you're right that it's possible that artificially produced black holes are ones where we would definitely think about the consequences for the universe we're producing, and may well be able to at some point manipulate the parameters in a way that has consequences for that universe. I don't think we're ever going to be able to fine grain our parameters on the child universe enough to ensure a deterministic outcome, though, because really there aren't a huge number of them. There's only in the high 20s maybe of basic parameters of matter in our universe, and it's their subtle interplay that generates this self-complexifying process that leads to something like us. But it doesn't necessarily lead to you and me here. What it does lead to is life forms on planetary bodies or moons that have liquid water oceans, that go through an evolutionary algorithm to generate life forms appropriate to those environments and so forth. So you might end up with something ape-like like us, or you might end up with something octopus-like, or something even weirder. But it won't be a deterministic outcome. Yeah.
On the notion of changing the parameters, it made me think. A previous question I had was, would there be changes we could make that would produce way more black holes? So you said that there's loads of black holes that our universe made, and then I wonder, could you produce more? And would we know how to do that? Or maybe it's obvious. Are there obviously ways we can make more black holes? Or the thing is, though, is that if you could make a universe that produces life, which then produces more black holes, then I guess that would be I'm getting ahead of myself. I wonder what you think, but
well, if you think multiple generations down the track, then just by producing universes that produce life that produces black holes, you're going to be. It gets very exponential very quickly. Yeah.
Okay.
Yeah, it's quite. The questions get very big very fast. I mean, I'm happy to stay inside our universe if that's too speculative for your audience, but
yeah. I mean, it's not too speculative. Go on.
Well, there's a lot you can say inside this universe. Like I think you can. Like my contribution to this theory was to make it a 3-stage model. So what you had with Smolin was a 1-stage model. There's just stars collapsing. It doesn't make a lot of predictions, and it does look a little speculative. The 2-stage model tells you a lot about the future, that intelligent life would be selected for, because you're going to push any intelligent life form will push energy efficiency up the efficiency slope, and the top point for that in our universe is small black hole production. You have to do a lot of small ones, because if you just do one big one sitting over there, everything that's more than a light year away from it or a light minute away from it is never going to get. It's no use for it. You have to produce a lot of small ones rather than one big one. just for energy efficiency, just for transmission, for just use. So, but that's also a futuristic thing. It's like we haven't seen it happen yet. Maybe it would happen. Maybe you can look for signs of it, but maybe we're early in the and also they'd be small, so it'd be hard to see them. They're very far away. 3 stars away, there's a small black hole. You're never going to see it. There's a bunch of them. You're never going to see them. So it's still speculative. The breakthrough, I think, the thing I was able to contribute to this, I think, is the reason I'm getting funding now, and it's the reason people want to talk to me, is that I realized there was an implication hidden in Smollen's original theory that nobody had teased out, that was incredibly important and really, really fruitful. And that was this. If universes reproduce through black holes, and if universes evolve, and there's a long evolutionary history, let's go back to the primal universes. What did they do? What can we say about the primal universes? All we can say is that they reproduced. How did they reproduce? Black hole, Big Bang. Did they do anything else? No, because anything else is structure and complexity, and we can't start with structure and complexity. Let's start with ultimate simplicity. How simple can you start? You can start with a kind of matter that's much more primitive than the very complex 90-something stable elements we have today. Some kind of matter that collapses, bounces, and expands again, right? That basically, by direct collapse, forms a very large black hole. Direct collapse, supermassive black hole. That the original proto-universe might just go into 2 universe, 3, split into 2 or 3 black holes, and that's it. And off you go. Evolution can kick off from there. But that's the direct collapse of supermassive black holes. We have supermassive black holes in our universe. There's a supermassive black hole at the center of every galaxy in our universe that we've observed. Anytime we've ever managed to look close enough at what's happening at the core of any galaxy within our sight line, you can see from the behavior of the stars and gas at the center that there is a supermassive black hole there. And when Smollen wrote his book, he didn't know that. They'd seen, I think, maybe 5 or 6 supermassive black holes. They were this weird thing that they vaguely had started to spot. So it's not really incorporated into his book at all. I realized that if you've got supermassive black holes in our universe, and when I'm saying supermassive, some of them are tens of billions of times more massive than our sun. Tens of billions. A lot of them are, hundreds of millions, tens of millions. Often they're millions of times bigger, but they're like many orders of magnitude more massive than our sun. Whereas a normal stellar collapse black hole is it's a few times more massive. It's 5 or 6 or 8 times more massive than our sun. It's, big stars collapse to make black holes. But these supermassive black holes are many orders of magnitude bigger, and they're very, very hard to explain if you think the only way you can make black holes is by a star collapsing, because you can't get a star that's tens of billions of times more massive than our sun. It's literally impossible. So how did they form? Thinking it through from first principles, they formed by direct collapse, because they always formed by direct collapse. They are the original way universes reproduced. Why would evolution come up with a new way of generating supermassive black holes when it already had one from the very first successfully reproductive universes, right? So that's going to be conserved. So the direct collapse of supermassive black holes is going to be how those supermassive black holes happen in our universe. And when are they going to do that? They're going to do that as early as possible. They're going to do it in the conditions that are as close to the conditions you found in the earliest universes as possible. When there aren't complex structures, you don't get stars, you don't get galaxies. There aren't complex elements. It's before the elements have been forged by fusion in stars. You've just got a bit of hydrogen and helium after the Big Bang, nice and smooth. We know how smooth it is from the cosmic microwave background radiation. It's very, very smooth. There's slight overdensities, but they're 1 in 10,000. Like, they're very small. My argument was evolution is going to be fine-tuned to generate all the supermassive black holes we see in our universe extremely early, inside the first 100 million years, from that very smooth gas. We see these overdensities in the cosmic microwave background, and they have a power law distribution. There's this very small number of very, very big ones, and there's a very large number of very, very small ones. It's exactly the same power law distribution as we see with the massive supermassive black holes. There's a very, very small number of very, very large ones that are tens of billions of solar masses, and there's a large number of smaller ones that are just, millions. And I'm saying they're the same thing. You're going to have the early universe is going to be fine-tuned so that there are overdensities that will collapse to form direct collapse supermassive black holes. Now, that's a big imaginative leap because it's hard to get the physics right to generate that kind of collapse. It requires really weird fine-tuning. Okay. But I'm saying you're going to find that evolution will give you that fine-tuning. And so that is the prediction I made before the James Webb sent back any data. So back in 2022, the James Webb was moving into position. It was going to send back data. And I thought, if this theory is, which I've been thinking about for several years and working on a book about, if this theory is true, it has to make predictions, or it's just speculative and I'm wasting my time. And thinking it through from first principles, I realized direct collapse supermassive black holes are the original way that the universe is reproduced. We have supermassive black holes in our universe. They must be produced by direct collapse. They have to happen in the earliest conditions after the Big Bang before structure formation. They can't be a consequence of structure formation because that's the wrong order in evolutionary terms, right? You can't generate supermassive black holes using lots of stars that require lots of complex elements. They have to precede all of that. And then they generate the conditions for all the more complex stuff later. So stellar collapse black holes, where stars collapse, would have been a later evolutionary breakthrough. And small technological black holes, which require an even more complex set of circumstances, require a much more complex periodic table, they would have been an even later evolutionary breakthrough. So what we're looking at under a three-stage model is there are three modes of black hole production. One is direct collapse supermassive black holes, which I predicted before the James Webb sent back any data, should occur in the first 100 million years, very, very early, preceding star and galaxy formation. The direct collapse supermassive black holes should then generate the conditions for galaxy formation and for star formation, and which allows for stellar collapse black holes, where stars get to the end of their life, and you get a lot more stellar collapse black holes per unit mass than you do direct collapse supermassive black holes, right? So a universe that had a lot of matter left over after the supermassive direct collapse black holes, and that explored the possibility space, and at some point there were universes that were able to turn those into little star-sized black holes. That was a very reproductively successful universe. It was much more reproductively successful than the universe that just split into a small number of supermassive direct collapse black holes. So that would be conserved, and the branch of the evolutionary tree of universes that produced direct collapse supermassive black holes and a lot more stellar collapse black holes would have been very reproductively successful. And then that explores the possibility space for matter. Matter gets more complex. Just blind pursuit. It's not positively affecting the reproductive success of the universe. It's just blindly exploring the possibility space. But when you get to life forms that can produce technological black holes, that's going to be a gigantically successful breakthrough, and that will also be conserved. So each builds on the previous one. You can't get the stars without the direct collapse supermassive black holes that optimize the conditions for that star formation. And you can't get the life forms without the stars that generate the elements that build out the planets and moons and life forms. So each builds on the previous one, but you don't have to leap to a complex universe in one go. This is one of the things that I really, really like about this theory. And it's one of the things that Smollen's original theory couldn't do in some ways. This gives you a step, which isn't his fault. He just didn't have the data. It gives you a step-by-step portrait of how an evolutionary algorithm just exploring the possibility space for matter will get you to something that looks awfully like this. And there's really interesting internal evidence of an evolutionary history just in things like the periodic table. One of my favorite things is if you look at, you can interrupt at some point if you, or are we good?
Mm-hmm.
Are we cool?
Yeah.
Okay. This is one I really, really like. There's a concept in evolution, in biological evolution, DNA evolution. There's a concept called exaptation. Exaptation is I think Stephen Jay Gould and who was that? Oh, what's that? What's her name? Another excellent biologist that came up with it a bunch of years ago. It's not Freddie. Anyway, Can't remember. It's got a very Hungarian kind of HV in it. Anyway, something like that. They came up with this idea of exaptation. Exaptation is when evolution adapts something that was already evolved for one purpose and uses it for a completely different purpose. It couldn't have got to that really complex, completely different purpose in one jump, but it doesn't have to, because it's able to build on something that was already evolved for a separate purpose. And the classic example of this is swim bladders in fish. The fish have an air sac inside them that they can inflate or not to move them up and down in the water. So if all the food is further down, they can let out some of the air, go further down. And they can adjust their height, and it makes it's more energy efficient. So you've got your air sac in your fish. When the first fish started to come up onto land, when you start getting these amphibious ones that are able to survive in air and water, they accepted the swim bladders, these air-filled sacs in the body, as lungs. They didn't invent lungs from scratch. Very, very difficult to invent lungs from scratch if you're a fish. Not that difficult to adapt by putting some gill lining on your air sac to adapt the swim bladder. So that kind of exaptation is a classic piece of evidence for an evolutionary history. Okay, we have evidence of exaptation in the evolutionary in our own universe, right? Because you have the CNO cycle, the fusion cycle in stars. Now, stars have two fusion mechanisms. Again, the fact that there are two fusion mechanisms is extremely suggestive of an evolutionary history, because the first fusion mechanism is proton-proton. It's a proton chain reaction, and it just requires protons. It just requires the simplest form of matter, hydrogen nuclei, protons. Right? That must have been the original fusion mechanism for stars, because when the first stars evolved, they can't have used complex elements as their fusion mechanism, because you don't have complex elements until you have evolved stars. Stars are the things that fuse the elements, right? So the original mechanism must have been proton-proton. It's been conserved. It's a perfectly good fusion mechanism. But we all have another fusion mechanism in stars now, which must have evolved later as the possibility space for matter was blindly explored by evolution, and you got protons finding. You had a basic parameter of matter set that allowed protons to stick together. That you got a weird, freaky version of a proton that we now call a neutron, which is a slightly more massive proton. That let them be close together, and you end up with elements, right? The other fusion mechanism in stars is carbon, nitrogen, and oxygen, the CNO cycle. And the CNO cycle acts as a kind of weird catalytic cycle that will generate lots and lots of elements and lots of fusion energy. That must have evolved later than the proton-proton chain, right? The CNO cycle. But you can see how it would evolve to help more efficient fusion, and therefore more efficient star formation, and therefore more efficient stellar collapse black hole production in universes. You can see how that works for the unit of selection that is the universe as a fusion mechanism. But then, what is biological life based on? What elements are the core elements for biological life? They're carbon, nitrogen, and oxygen, which would have evolved already as a stellar fusion mechanism, but got exapted by evolution as the basis for biological life. So you didn't have to invent the chemistry of biology from scratch. Some of it had already been evolved in as a fusion mechanism for stars. That is entirely suggestive. It's not conclusive. It's not the kind of evidence that physicists like, but it's definitely the kind of evidence that biologists like, because that's what we see in DNA evolution.
It's interesting the way this kind of thinking can explain fine-tuning and the complexity of the universe that we see. Yes, more complex elements being created later. And I mean, that's, I guess, within a universe, I suppose. Like, we know we don't get any carbon and metals and things without supermassive. Wait, well, from stars and
Stars.
yeah, and supernovas. But then
Yeah,
across, go
which
on.
is also very interesting. The fact that stars build elements at the bottom of a tremendous gravity well and then distribute them out into the interstellar medium, out into the hydrogen flowing in from the filaments, and enrich them so that, that you can have a second round of star formation that has those elements from the start, and then those blow up in supernova explosions, distribute, and to form a third round of stars, which has a lot more heavy elements in it that it can then build out, and plus you get neutron stars merging to make gold and lead and uranium and the really heavy stuff. So and distributing it out. So the fine tuning of matter required to not just make this stuff, but distribute it out from the bottom of gravity wells is another example of what looks awfully like fine tuning. It's very, very interesting that you get these weird, not exactly flips, but you get this kind of collapse to expansion as a direct result of the way the basic parameters of matter are fine tuned in our universe. And that's what allows for life, because you can't get life around a first generation star because it just hasn't generated enough elements. There aren't enough heavy elements to give you planets and life.
So then, would you say? So yeah, would you say in the history of universes, then you wouldn't have wanted them to just slowly produce loads of stars? You need to sort of have a process that can make bigger stars and like just the way you kind of frame it is that first there would be supermassive black holes. That's a very simple, easy way to make new universes, and then you keep those, and then they would still be important though later on. But I'm wondering how. I'm wondering why they would. I guess they would still be around. Because they're
black holes.
Yeah, I guess they're conserved, as you said.
I can explain why if you want.
Yeah, okay.
They're what build out galaxies. So this is a piece I'm working on, which I'm going to put online soon, but I haven't actually put it out there yet. But I'm happy to talk about it now. So supermassive black holes are what build spiral galaxies in my model. This is an extension of blowtorch theory. I know you've read some of blowtorch theory. This goes into detail on the spiral galaxy formation thing. Here, listen to this. If you think through from first principles, again, how this plays out. Supermassive black holes, right? If they form first, as I think they do, and as it looks like they do according to the James Webb, because the James Webb is, the further back it goes, the more proportionately dominant the supermassive black holes are in early galaxies. And my argument is if you look back far enough, we can't yet. But you're actually just going to see the supermassive black holes form first. So here's a mechanism for spiral galaxy formation driven by supermassive black holes. Just thinking through logically what happens if you develop the supermassive black holes first by direct collapse. Your supermassive black hole forms by direct collapse in the early universe. The plasma in the early universe, if you go back to, let's go back to redshift 35, right? So you're about, 80 million years after the Big Bang, something like that. The mean plasma density, the density of all the little bits of gas and plasma floating around the universe at that redshift, that early after the Big Bang, 80 million or so years after the Big Bang, is about 45,000 times denser than today. 45,000 times denser. Because if you redshift 35, the universe is 35 times smaller that way and that way and that way. In all three dimensions, it's 35 times smaller. So it's about 45,000 times denser. When you get your supermassive black hole collapsing, it brings an awful lot of matter with it, a lot of gas, a lot of plasma comes down with it. So it's born surrounded by an even denser again cloud of plasma, right? And that plasma, some of that falls into the black hole, falls into the accretion disk around the black hole because it's a huge gravity, well. And it forms an accretion disk, which is that hot donut of, if you've seen any science fiction movie that has black holes, you'll see this hot donut of blazing plasma very close around the supermassive black hole. It spins at close to the speed of light because angular momentum is conserved. So as it falls in, this is how you get so much energy out of black holes, right? So you have this spinning at the speed of, close to the speed of light, accretion disk of plasma. So it's charged particles spinning at close to the speed of light around the supermassive black hole. That's an unbelievably powerful dynamo, because you spin charged particles at that speed and you have one hell of a dynamo. And it generates these two jets. We know it generates these jets from the local universe, where we see this happening with black holes in nearby galaxies. So we know this happens. It generates these jets, but if it generates these jets at the density of plasma that's surrounding the newly born supermassive black hole back then, the jet will stall after a few kiloparsecs, a couple of kiloparsecs, few thousand light years. It will stall because it's pushing through very dense plasma, and eventually it's compressing the plasma. It's losing energy as it pushes plasma out of the way. And once it stalls, it starts to backfill. The jet is still firing. There's still plasma coming into the jet, but it's firing into this very dense plasma, and the jet spills out into it. Now, the jet has a helical magnetic field. We know it has a helical magnetic field. That was realized back in the 70s or 80s, and since then we've observationally seen it, because the field lines from this charged jet coming out of the accretion disk are being twisted by the spinning accretion disk and black hole at the center. They're getting twisted as they go up, so they're twisted into a helix. So the helical field lines peel off along with the plasma, because they're frozen into the plasma of the jet. They peel off into this, what becomes this overpressured, highly overpressured bubble or cocoon inside the plasma. So it's pushing out the plasma with this highly overpressured region, which isn't dense but it's unbelievably hot. So what the jet is doing is mostly pumping energy into this increasingly large bubble of unbelievably hot plasma that is not very dense because it's so hot that everything's pushing everything apart, and it's pushing out this huge cocoon of plasma around itself. But it's also embedding these helical field lines in this cocoon of plasma, right? Until eventually the pressure is too much and it chokes off the jet. The jet stops doing it. But now you've got this couple of kiloparsec overpressured plasma bubble with a cocoon, a really dense cocoon of plasma around it that has been striped with this helical magnetic field. That bubble cools down remarkably fast in this era, as you would expect if it's a fine-tuned universe we're living in that's designed to do this, because there's so many photons from the cosmic microwave background radiation at that era, and the photons are able to take energy out of the electrons in the plasma. So it cools down remarkably fast within a couple of million years. And once it cools down, the whole cocoon, the whole huge, dense, now helically, magnetically fielded cocoon of plasma collapses, right? And when you collapse, and it collapses to form a disk, because that's your classic Zeldovich pancake, where, there's a preferential axis of collapse with these big bubbles, and it's going to collapse to form a disk. A helical electromagnetic field in a 3D space like that, when you collapse a 3D helical magnetic field down to a disk, you get a spiral. So you're going to have a very, very strong spiral magnetic field in the collapsed cocoon, in the disk, right? So now you've got your protogalactic disk with a spiral magnetic field in it. I've run the maths on this, and it should have a field strength that's roughly in the milligauss range. So, thousandths of a Gauss. That's actually a lot, right? It's about 3 orders of magnitude more than we have in the Milky Way today, which has a micro Gauss field. So you've got this very, very powerful magnetic field, spiral magnetic field in the disk, right? And a milligauss field is enough to actually freeze that disk of plasma into solid body rotation. It takes maybe a few million years, maybe tens of millions of years, not many though, relatively quickly, because the Alvan speed, the speed at which the electromagnetic field can spread in a disk at that era it's pretty fast. You've got this compact disk, extremely high field, and that overwhelms the density. It scales with the square root of the density, but the field strength is so high that the square root of the density isn't enough to overwhelm it. And so you get a very fast Alvan speed. So over a couple of rotations, the whole thing locks into solid body rotation. So now it's spinning like a vinyl LP. It's all moving at the same speed, right? that field unlocks over the next tens of millions of years. It cools down. It starts there's a bunch of reasons why it fades over time, but it does fade over time. And as it fades and unlocks that plasma, it has over that, having locked into solid body rotation, a lot of energy has gone from the inner region to the outer region. It now has to adjust. The plasma at each radius has to adjust to the fact that it's not locked together anymore. So what happens is it spreads out. So you get, because it has to balance centrifugal force with gravity. So it spreads out, but the plasma is all moving at the same speed. So as it spreads out and cools down, you get star formation. The stars are born moving at the same speed as the plasma, but the plasma is all moving at the same speed. So those stars are now all moving at the same speed. You've got a flat rotation curve. You've got a spiral magnetic field and a flat rotation curve. And that is going to happen if you get supermassive black holes forming first with dense plasma in the early universe. This is just like first principles thinking. What will happen? That's what will happen. You will get spiral galaxies. What's happening in the core, though? What's happening in the center of that spiral galaxy? The cocoon around the edge collapses. You've got your spiral magnetic field, and you've got your solid body rotation. But right in the center, it's falling back on top of the supermassive black hole. It's falling back on top of the accretion disk. So that plasma doesn't maintain its spiral magnetic field because it can't. The thermal energy being pumped into it by the accretion disk buggers it up, and you get chaotic hot. You get a chaotic hot collapsed cocoon core around the supermassive black hole, right? When that cools down over time, that will be the bulge of the spiral galaxy, and the rest will be the disk. So it explains the bulge, the disk, the spiral magnetic field, and the initial flat rotation curve. That's why supermassive black holes are conserved. They build spiral galaxies. Also, what does the hot central bulge look like when the plasma cocoon collapses on it and is cooked by the accretion disk over the next tens of millions of years? It looks like a little red dot. It looks like a little red dot. It is exactly the spectrum that we're seeing in the little red dots that the James Webb Space Telescope is seeing in the early universe. Right? Nice, huh? It's got the same spectra because you can't see X-rays coming from the accretion disk because they're in this very dense cocoon that's like light months wide, about the density of maybe the solar corona. It's not super dense. It's not stellar dense, but it's really dense compared to open space. And there's enough of it to soak up all the X-rays. And you will see things like highly ionized oxygen, highly ionized neon, stuff like the stuff that we are seeing in the little red dots is the stuff you would see if you had X-rays from a hidden supermassive black hole smacking into the gas. So the X-rays aren't coming out, but you are seeing ionized gas that has been ionized by those X-rays. It's exactly what we're seeing. So if this model is correct, it explains spiral galaxy formation, the bulge, the kinematics of the bulge, where the stars move randomly because it's been thermalized to FEC. The disk, where the collapsed helical 3D magnetic field has become a 2D spiral field and has not been disrupted far enough out from the supermassive black hole. The flat rotation curve and the spectra of the little red dots. So if I'm right, the little red dots that we're seeing now are the glowing cores of these collapses. There should be spiral plasma disks, if you go back far enough, locked in solid body rotation, but later on a little bit more spread out and cooling down and forming stars outside of that. But at the moment, they should be, again, I ran the maths on this, and they're going to be below the visibility threshold. They're going to be far outshone by the point source of the collapse core on top of the accretion disk and the supermassive black hole. So, but if we get better observational data, we should, I think, end up seeing dimmer spiral disks around those little red dots. So that's where I'm at the moment. It has great power.
Go on. Yeah. I wonder how people would explain how spiral galaxies form normally, right? So do they?
Oh, I can tell you, sure. Yeah.
Sure.
Well, no. What's your impression of how they explain it?
don't know how they explain it, but I suppose your explanation is something like the supermassive black hole in forming the galaxy forms around it.
Yeah.
So I mean, I guess another way maybe like the opposite is something like stars could form and loads of them could just happen to come together. And I mean, I'm not sure how. I don't know. I'm not a cosmologist. I don't know how
Yeah,
to explain it, but
well, the current model, this is how they currently explain it. The current model is lambda cold dark matter. It basically says it says galaxy formation is bottom up. It's through multiple rounds of mergers of little clumps of gas and stars, and they up to 20 rounds of mergers are required to get you to something that looks like a bit like a galaxy. And then over about 1 billion years, a very weak dynamo builds up a nano Gauss, a billionth of a Gauss field, up to a millionth of a Gauss field over 1 billion years. That's how they say it happens, right? Whereas I'm saying it happens dynamically in one highly energetic process without mergers. So there's an enormous delta between what I'm saying and what they're saying. But they're running out of time for their model. They're running out of time. The further back we go, the earlier we're seeing spiral galaxies. My model explains it. Their model doesn't. We're seeing spiral galaxies in the first 500, 400 million years, which I would say, yes, you will see, and which they would say, you shouldn't, and also that they shouldn't have spiral magnetic fields by then. They shouldn't have structure by then. I'm saying they're born with structure. They're born with structure. One of the things that makes me confident that I'm onto something here is when I predicted this I didn't. Now I got to tell you that new version I just gave you of spiral galaxy formation is fairly recent. When I did my original predictions in 2022. I was a bit hand wavy about how spiral galaxies were formed because I knew that the logic of evolution said that the direct collapse supermassive black holes had to do it, but I had a fairly primitive model involving just shock waves from the jets shocking out star formation. Right, it was a relatively primitive model. I think I've got a much more sophisticated model now that gives you the spiral magnetic fields and the flat rotation curve. I can't maintain the flat rotation curve. I don't have a model for how it's maintained over billions of years. If you want, you can use dark matter to do that. Fine, be my guest. I do think we will come up with an explanation for it because it's harder to generate the initial flat rotation curve than it is, I think, to maintain it over time. And I think if we've cracked how they form with a flat rotation curve at the start, we will definitely crack how it's maintained over time. But for now, if you want to throw dark matter out, fine, be my guest. Go on.
Do people use dark matter to explain how galaxies come together, have that complex spiral structure, and
they use dark matter to solve all the problems that they don't know how to solve? And unfortunately it's become a kind of it's an easy thing to reach for, and it's become, I think, a crutch for the field. I think what they have failed to fully explore the possibility space for baryonic matter, for ordinary visible matter, because they can always lean on dark matter. And dark matter can do whatever they want it to do. Sometimes they have it weakly interacting. Sometimes it doesn't interact at all. It does whatever they need it to do to explain the phenomena they're looking at. But what they're not doing is they're not looking at the extraordinary potential for baryonic matter to self-structure if it's fine-tuned. Like what I'm talking about here, the blowtorch theory that you mentioned of structure formation, I just gave you how you can get the jets from supermassive black holes to basically, what would you say, to channel energy into structuring galaxies, right? Once you've done that, once you've formed your galaxy, you can then, if the jets switch on again, they're going to be blasting considerably further distances because they're no longer going through that thick cocoon that they were kind of born with. That's been dealt with. That's formed the spiral galaxy. Now they're firing, they're going to be going. I think they can build out the voids and filaments. They're doing it early enough that they can build out the voids and the filaments that we see in our universe. Because 80% of our universe is voids. 80% of our universe doesn't have really anything much in the way of stars and galaxies and gas in it. It's pretty much empty. It's like below 10% the mean density. Like, so 80% of our universe is below 10% the mean density of the rest of the universe as a whole. It's really, really low. And about 20% has half the matter in it, that's the filaments. And then about the other half of the matter is in the 1%, that's the nodes where the galaxies all cluster. And the filaments feed hydrogen into the nodes where the galaxies actually are. And they feed it in over long periods of time. So my argument is the jets are essentially forming the reservoirs. They're blowing open the cavities that will early enough that those cavities are eventually going to merge and expand with the expansion of the universe and give you the voids that we see today. But they're in doing that, in blowing apart, in creating these huge cavities, they are pushing the plasma into reservoirs, the filaments, which then feed back over billions of years into the nodes, so that you can have ongoing star formation over multiple generations, which is what you need to build out multiple rounds of star formation in order to build out full periodic table, in order to have life, planets, life, and technologies. But it's a multi-step process to build out life. You don't get the full 90-something stable element periodic table in one go. You start off with none of it. You start off after the Big Bang with just hydrogen, helium, and a trace of lithium. It all has to be built by stars, and then it takes multiple rounds of star formation to get a star like our own. Ours is a third or fourth generation star, the sun, which then has enough matter to do life. So to do that, you need a fresh source of hydrogen, which comes in from the filaments. It's coming in all the time, gravity feed down to the dense nodes, to feed into those galaxies, where it is enriched by the supernova explosions, where they blow the elements that they've just built in their cores out into it and enrich it, so it can cool and condense in the arms of the spiral galaxy in the stellar nurseries to build out more stars that can go through the same process at more filamentary gas coming in, more supernova explosions, and over billions of years build out the full periodic table, distribute it, and then build out planets, moons, and life. And it is a very complex, self-assembling, self-complexifying system. It's got a circulatory system. It's got basically what you would say are things which are analogous to metabolic pathways in biological life. One of the key things about a biological system, I think Prigogine said this, I believe it was, I'm not sure, it might have been Prigogine, that the energy that moves through a system in a biological system organizes the system. That's the difference between an evolved biological system and a chunk of rock or a piece of hillside or whatever. The energy that moves through a rock disorganizes the rock usually. It gets wet, it gets sunshine, it gets hit by lightning, it falls apart, right? But the energy that moves through you or a rabbit or a tree organizes you and the rabbit and the tree. The energy that moves through the system organizes the system. And my argument is that in an evolved universe, the energy that moves through the system organizes the system. That you will get direct collapse supermassive black holes. They will generate accretion disks and jets. The jets aren't random. The jets are metabolic pathways for energy that will build out the structure of a spiral galaxy. The spiral galaxy isn't random. It's a set of metabolic pathways. It's got a spiral magnetic field. The spiral magnetic field means it gives it arms. It is able to switch on plasma by, if you heat gas, if you heat hydrogen, you ionize it. If you ionize it, it's charged. If it's charged, you can move it using magnetic fields. Once you've moved it to where you want to move it, if you can cool it down, which you can do by enriching it with oxygen or carbon or whatever, because they act as coolants, right? They soak up photons and let the gas cool. Now you've got molecular clouds, and now you get them collapse to form stars. You can switch off the electromagnetic charge on plasma by just letting it cool. And now you can just use gravity to collapse it, and now you can turn it into stars, and then you can turn it into planets, and you can turn it into life, right? So you've got a circulatory system. You've got essentially a universe behaves like an evolved organism traveling down a developmental path where the energy that moves through the system organizes the system. And the system builds out things that are analogous to organs. They have functions. A spiral galaxy has a function. A supermassive black hole has a function. The function is to build the galaxy. It builds the spiral galaxy. Now the spiral galaxy has a function. The function is to build stars. It builds the stars. Now the stars have a function. The function is to build out and distribute the periodic table. It does that. And then they form planets. Now planets have a function. The function of planets and moons is to generate the conditions for life. Now life has a function. Life's function is to move up, explore the possibility space in its piece of territory and move towards intelligence and complexity. And once it's intelligent, it's able to manipulate matter and build out technologies. And technologies will eventually build out small black holes and help the universe as a unit of reproduction reproduce. At every stage there, mass energy has a function. It's doing something. And it's doing something that benefits the organism, the unit of selection that is the universe. And that model, that picture of our universe makes enormous, overwhelming, coherent sense. And there's no other model out there makes anything like that amount of sense. And people that dismiss this without having read anything about it, because that's usually the people that dismiss it, it's much harder to dismiss this once you've read all the work. The people that dismiss this are making a colossal mistake, I think.
It's quite amazing, the structure of the universe. In reading your work and seeing the webs of filaments, and it's a network, and then so it's and galaxies are connected to other galaxies, and then because and you made predictions about it, which is really cool. Yeah. That we would find stars and galaxies earlier than people predicted. Because people predict that you just get stars forming quite slowly. Because
I particularly predicted that you would see rapid, efficient galaxy formation around supermassive black holes. That was my particular specific. I was saying you are going to see very rapid, very efficient galaxy formation around supermassive black holes. Because the existing model, which I mentioned before, but I'll go into more detail on, I call it. I'm starting to call it the bump and clump model, where like lambda cold dark matter says it's just little patches of stars will form, and then they'll bump into each other through, there'll be gravitationally attracted, and they'll merge, and you just get multiple hierarchical rounds of mergers. It's all very random, it's all very arbitrary, and it takes a long time. And it doesn't predict anything like what we've seen. And now they're of course they're modifying it to say, well, they must just merge faster than we thought, and they merge a lot faster than we thought. And they have a lot of, they've done a lot of after the fact adjustment so that they can say the theory isn't broken, but they didn't predict anything like what we saw, and I did. So, make your own mind, make your own mind up. The thing is, I'm not, I do not have the domain knowledge that they do. So the fact that the theories I made from a relatively naive perspective, I've learned an awful lot more in the 2 or 3 years since then. I know a lot more, magnetohydrodynamics than I did in 2022. But the fact that I was able to make extremely specific theories about very early, very rapid spiral galaxy formation, driven by supermassive black holes that come first, so that you should see, the further back you go, you should see more and more, galaxies should be small, compact, efficiently built early, with ever more dominant, supermassive black holes the further back you go. That's exactly what we've seen. The fact that I can do that with a relatively poor background in the field speaks very, very highly of the theory. You see what I mean? Mm-mm. There's something to a theory that is so robust it can survive me working on it. You know what I mean? And there's something wrong with the basic paradigm in the mainstream, if the mainstream have had such a catastrophic failure in predicting what they're seeing in the early universe. There's something profoundly wrong with their paradigm. And I think it's what's wrong is they're assuming a random arbitrary universe where the basic parameters of matter have no meaning, have no consequences, nothing has a function. And with that basic assumption of randomness and arbitrariness, they're consistently wrong. They're consistently wrong. And they have been for decades. I wrote a piece that's on the Substack called "In Cosmology, All Our Mistakes Lean in the Same Direction." We have been consistently, for the last century, blindsided by complex, efficient structure formation at every scale as far back as we can look. It's always more orderly than we expected. It's always more efficient than we expected. It's always more structured than we expected. And yet we never adjust our theory to take into account the fact that we keep failing in the same direction again and again and again and again and again. And that is almost always a sign that there's a dogma underlying the field that is unexamined. It's not inside the theory, because if it was inside the theory, they could critique it. But it's not inside the theory. And the assumption is we live in a random, one-shot, arbitrary universe where nothing means anything. None of the basic parameters have settings that have a meaning which has a consequence. And I think that's a sociological truth about cosmology and astronomy and astrophysics that comes from the fact that science broke with religion back at the time of Galileo and has been terrified ever since of saying anything that would imply a religious explanation or God as an explanation. And the interesting thing about evolution is it can look like God if you're not expecting evolution, So I think they're terrified to say, this looks meaningful, this looks directional, this looks like it's going somewhere, this looks designed, because they think that would put them on the same side as the creationists and the intelligent design guys who say God made it so, It doesn't. It puts them on the side of Darwin. It's what they're seeing as evidence of evolution. There's design. It was designed blindly by an evolutionary algorithm, just like giraffes, just like their children, right? Your child is directional. It's meaningful. It's also a product of evolution. The universe is directional and meaningful, and it's the product of evolution. And a sufficiently sophisticated product of evolution has astounding qualities, And that's where we're at, I think, now. We're stuck with a sociological problem inside science that makes it very hard for them to acknowledge what they're actually seeing.
So do you think that across evolution of different universes was reproductively successful universes create more universes, that there would be slight changes like in the mass of different electrons, fundamental particles? So then, I wonder how that works. So, would you want to? What would you want to? What if the electron was way heavier or something? Okay. What would happen?
I have some thoughts on this. I think it used to be. Here's something really interesting about the Standard Model, right? It's got 3 charged leptons. It's got 3 kinds of electron. It's got 3, negatively charged, leptons. One is the electron that we're familiar with. One is the muon, which is basically a really massive electron. And one is the tau, which is a really, really massive electron. That makes sense in a 3-stage cosmological natural selection model. If you go back to the original universes, that just reproduced through direct collapse supermassive black holes, all that mattered was mass. To optimize in that era required the heaviest electron you could get, heaviest proton you could get, just like big, heavy particles, shove it, have as much mass in as small a territory as you can and have it collapse, right? So the tau, which is a very, very massive electron, could be an evolutionary hangover. It's still implicit in the quantum electron field, right? You can still generate one if you have enough energy, but you don't need them now because our universe is doing other things. But the tau would make sense as the original electron from the supermassive black hole direct collapse era. The muon could well have been a breakthrough, a variation that helped optimize for not just supermassive direct collapse black holes, but also stellar collapse black holes. So it would help stars collapse. What you want is a heavy electron, but not as heavy as in the supermassive only era, right? So a freakish mutation universe that had a less massive, but still quite massive electron might not be as good at producing supermassive direct collapse black holes, but it could be better at producing, in the mass that's left over, little star-like collapses, right? So that explains the muon. But when you get to life, technology, you need a more complex periodic table. So a freakish mutant universe that came up with a very lightweight electron is suddenly able to explore the possibility space for complex elements, for a 90-something element periodic table. You can't do 90-something elements of the periodic table if you've got a tau as your electron. It's gigantically massive, and you can't do stable atoms with it. So you can actually, I argue, we have evidence in our universe for an evolutionary history for electrons. That is highly speculative. I'm perfectly happy for people to disagree with me on that one. That one is not obviously true, but it's unbelievably interesting. It's very suggestive, right? It's very suggestive.
Go on.
Yeah, go on.
Well, do you think that there's more structure than early or in the universe, or just in general, because of this evolutionary history then?
Sorry, say that question again.
There's more structure in the universe
now
or in the past. I mean, yeah.
Well, there's way more structure now. I think that like the earliest universes just had no structure at all because they didn't have anything to structure with. You didn't have a periodic table, you know? You had something a bit like hydrogen, you know? You had something like a proton and an electron in the very earliest universes. And then as the possibility space gets explored, you get something a little richer. You get more complex elements, and now you're able to do stars. And then you've got the periodic table evolved, right? Under this model, there's universes that just have hydrogen. There's the earliest ones. But as you get up to stars and that, you get hydrogen and helium, and you get helium and maybe lithium. And then you get hydrogen, helium, and you get carbon and nitrogen and oxygen. And now you've got a very rich stellar environment. You've got some very rich stellar structures now. And then you get this breakthrough into even more complex structures. As more of the periodic table gets built out, evolves, you get biological life. And at each stage, before the breakthrough into actually reproductive success, these were probably not very successful universes. In the same way that mammals were just little mice running around in the dark during the time of the dinosaurs, we were not particularly successful. But eventually you get this breakthrough into intelligence, and off you go, man. So I think, the universes that were exploring the periodic table up until the breakthrough to life were probably just kind of minor branches that were just like weird, they were still producing a lot of stellar collapsed black holes. They were still reproducing, and a lot of, some supermassive black holes they were reproducing, but they didn't take off until they actually got life to the point where it could produce small black holes. And that could have taken an incalculable number of generations to do. It's an amazing breakthrough, but it doesn't have to do it from scratch.
It's interesting when you say that there's purpose to the universe then, but
to the extent that there's also purpose to a dog, there's purpose to, there's purpose. If you've got life, and certainly once you've got consciousness, you can't say there isn't purpose, but you can do it without God. You can essentially, you don't need an external, inexplicable God figure here. The universe on its own, with its evolutionary history, in a way performs many of the functions that God performs in a lot of cosmologies or theologies, but without the problem of explaining God. It strips away an entire superstructure of inexplicable weirdness. Evolution is weird enough, but it's explicable. Evolution is weird enough to give you consciousness-packed, universe-sized organisms. You don't need a whole other layer of weirdness on top of that. It's already weird enough, and it's purely scientific. One of the things I love about this theory is it's so conservative. It's more conservative than the current mainstream model. It's saying all you have is matter, and evolution. And that's all. And you don't even need extra particles. I'm trying to do it without dark matter. I honestly think dark matter is going to go away over the next 20, 30 years, because I think each aspect that is currently being explained with dark matter will be explained through the fine-tuned behavior of baryonic matter. Self-structuring, self-organizing universes behave in kind of weird ways. The basic parameters are set to levels that interact with each other in ways that are that seem tremendously unlikely until you actually work it out, and then you go, oh yeah, that's how it does it. The solar corona. We've been puzzled by the solar corona for a very long time. It's clearly obeying the laws of physics. It's not doing anything weird, but it's sitting at 1,000,000 degrees above the surface of a sun that's at only 5,000 degrees, right? So you've got a thin layer of plasma at 1,000,000 degrees above the surface of the sun, which is only at 5,000 degrees. That's until you work out the fine-tuning that was required for energy to do that. It's just really, really weird. And we keep coming across things like that. Highly, dynamic out of equilibrium systems, homeostatic dynamic out of equilibrium systems where energy is highly rooted to perform functions, which looks to me like a sign of an evolutionary history. But
Go on.
But at the moment we just throw dark matter at everything because it means you don't have to think about it.
Can we interact with our parent universes? Maybe, is that possible?
I love that question, and I don't know the answer. It's an unbelievably big question. It's actually the kind of question I do not address in my work because it freaks people out and it makes them think I'm in the land of woo now, and they run away scared. So I don't. But I do think it's an incredibly. It will become an incredibly important question once we've nailed down I just want to explain material reality right now. I'm just trying to just say there is a theory that will give you a self-organizing, self-complexifying material reality inside, the membrane that is this bubble of space-time. And I just want to explain that for now. But as soon as that's done, I think people will have to go wild on these questions. Yes, if there's a parent universe that knows it generated us, if intelligent life forms generated this universe, which is the most likely outcome if this is true, can they communicate with us? Can we communicate with them? Is there an unbridgeable barrier at the bounce between black hole and Big Bang, or is it bridgeable? I don't know. It's the trouble is that is territory which is totally speculative. I don't have any clever ideas there. I do think it's a brilliant question. I would love other people to explore it. I'm not going to explore it right now because it would put me into territory that would get the material reality theory I'm working on dismissed. The one problem this theory has, which I completely understand, is it's an outsider theory of everything that says it explains, reality of the universe better than the existing theories. And that is almost always not true. There is a long history of theories of everything that turned out to be bullshit. And there's a lot of very sloppy thinkers in this space. And some of them are lovely, lovely people, but they have fallen in love with an idea and they're not rigorous enough with it. And they strap on a lot of slightly woo things that they like the sound of and the feel of and the vibe of, and it kind of trashes their ability to actually do science. And I'm trying very hard not to do that. For instance, I can't maintain the flat rotation curve for galaxies right now. I can have them born with the flat rotation curve. I do not have a mechanism that explains how you maintain that over billions of years. I don't know how to do it. So I am prepared to say the best theory for that right now is still cold dark matter. I have not succeeded in coming up with a better explanation for that. And there's a bunch of other stuff. Gravitational lensing. I have not come up with a better theory. It's fine. But I think you should probably give me extra credit on the stuff I am claiming, given that I'm not claiming everything. I have not explained everything. There are areas where I can't come up with a better explanation than the current model. I just think the current model has a fundamental error underlying it that means it will never be the sufficient theory that evolution, I think, can become. Evolution may well end up working hand in hand with cold dark matter. It's quite possible there has to be a hidden mass that is part of this explanation. I'm totally fine with that. It's not necessary to believe in or disbelieve in cold dark matter to take up an evolutionary theory and run with it. It's at the moment, it's not clear whether it will be able to replace dark matter. My gut feeling is it will. There's an inability to get it into focus about cold dark matter that makes me feel it's just epicycles and it's going to go away. But I might be wrong on that, and I'm totally prepared to admit I might be wrong on that. I'm not worried about that. That's not the argument I'm making. I'm not making an argument that I've proved dark matter doesn't exist. That isn't true. I have not done that. What I have done is I've provided a far better explanation for spiral galaxy formation, better explanation, I think, for voids and filaments, better explanation for self-complexification, better explanation for the CNO cycle and the proton-proton chain existing as fusion mechanisms, better explanation for why the CNO cycle in fusion happens to use the same elements that are the basis for biological life. An interestingly provocative explanation for why there's 3 charged leptons, each less massive than the previous one. Yeah. I think my big contribution is saying supermassive black holes are the original reproduction mechanism. They form by direct collapse. They do it in the very early universe, and that's what you're going to see. And they're going to build out galaxies around themselves very rapidly and efficiently. That's my contribution. If I'm proved wrong on that, then you can probably dismiss me. But all the evidence is looking very, very good.
A final thing. This is a bit of an absurd question, perhaps, but would a supermassive black hole that forms a baby universe, would that be bigger than a black hole that's just from a star?
That's a great question. Actually, I'll tell you, there's kind of almost 2 objections that I get a lot. So I might as well deal with them, because some of your viewers will be doing these objections, because I know this from talking to lots of people. These are the 2 objections. One is, but won't the universes get smaller and smaller as the black hole that produces them has less and less mass energy going into it? And that isn't actually the case. One of the interesting... Now, it's possible that more is different and quantity has a quality all its own. It is possible that the universe is generated by supermassive black holes might be in some ways different. But it's not necessarily the case that you get a smaller universe because you've got a smaller starting black hole, because universes are actually energetic. They're flat. Like the positive mass energy and the negative gravitational energy in the universe net out to 0. You could net out all of the energy in our universe essentially to 0. Somebody ran numbers on this at one point and said, I think I'm not entirely sure to what extent they were joking about the precision here, but that it takes about 10 kilos of matter is enough to generate an entire universe, a full-sized universe. It's because it nets out to 0. In the same way you can imagine, if you produce, matter, antimatter particles are appearing all the fucking time in the quantum foam, they, as long as they're balanced to 0, it doesn't matter. But the mass energy of our universe should net out to 0. It should be possible to make a universe from nothing. This is not controversial. This is something that Hawking argued for. You can make a universe out of nothing. There's entire books written on it by pretty straightforward mainstream physicists. So yeah, you should be able to get a full-sized one from a. But yeah, would there be a difference in the 3 generations? I don't know. My feeling is that once consciousness is involved and you are consciously generating black holes that will generate universes, I feel that there's probably a way to do some tuning there that you would kind of be morally obliged to do. And so I think that those universes produced by intelligent life forms will be, genetically engineered. They'll be domesticated. They'll be whatever analogy you want, but they won't be exactly the same as black holes born in the wild. Mm-hmm. That's my feeling, but I don't know. Again, this theory generates an unbelievable number of really important and interesting questions. And it's wide open for exploration. If anyone wants to explore this, if there's any scientists, if there's any young, PhD students out there, like just bored with their field and thinking, I want to do something really interesting, and they're getting ideas watching this and listening to this, get in touch with me. I'm putting together an evolutionary cosmology working group. I'm going to be moving to the United States early next year. I'm putting together an evolutionary cosmology working group. I seem to have some funding. It's what I'm trying to do is I want to generate an entire new field, essentially from scratch, because the existing fields are inadequate to do the job. It's not their fault. They're just hyper specialized, and they're too far apart. If you look at the graph, there's like a lot of amusing graphs out there of which papers in which fields cite which other papers. And if you look at it, evolutionary biology is way over here, and astrophysics and cosmology are way over there, and they know nothing about each other's fields. They don't read each other's papers. They don't know each other's foundational principles. So I'm having to essentially create a field from scratch. And I think if we get this right, you could end up on the frontier of the most important new science of the 21st century. So get in touch.
Yeah, where would you want to point people? Your Substack and where else?
I'm writing a book about this. This started out as a book, and it's become this research project, working group, crusade. But I'm writing a book online called The Egg and the Rock. The Egg and the Rock, because the argument here is almost a philosophical one. I have a slight background in philosophy. A philosophical one between, does our egg, over time, does it appear to be behaving like an egg, developing upward into complexity, or like a rock, simply decaying? And I think it's behaving like an egg, not a rock. And I think that needs an explanation. I think evolution is the explanation. So The Egg and the Rock is my Substack. Come there, comment. Email me. It's just my name, my first name and last name at gmail.com. Just email me. Very straightforward. Get in touch. We need a lot more people working on this. We need people from every field working on this. There's so many. I didn't even get into stuff like mineral evolution, like Robert Hasen's amazing paper from a few years ago, where he realized that he's a mineralogist. He realized that nobody knew how old the minerals were on Earth, like when they first appeared. All the various rocks and crystals and the types of stone. Nobody actually had a chronology of when they first appeared, which was like kind of shocking to him. This is only about 14, 15 years ago. And so he got a bunch of geologists and geochemists and petroleum guys and asteroid experts together, and they put it together, and they realized, oh my God, look at this. They're like the cloud that forms the Earth has about 15 or 16 minerals in it. And now we have probably 5,000 or 6,000 minerals on Earth. And this complexification of minerals happens in this really beautiful way. And there's a huge amount of self-complexification of mineral life on Earth, which is far more complex than on any other planet, right? That we've observed close enough. This complexification gets to a point where it enables life to happen, and then life drives the complexification after that. And then life gets to a point where it's able to go from anaerobic to free oxygen, and that complexifies it again. And it's all one process of self-complexifying and self-ordering. You can't really, in a way, separate it out. If you look at it as a graph, there's a chemical logic playing out that leads to life. And then there's a chemical logic to life that's playing out that essentially leads to technology, that leads to intelligent life that can then take other elements out of the periodic table, out of the core, and out of the mantle, and out of the that have been spat up onto the crust of the Earth, and turn them into things. And we are now constantly generating forms of material on the surface of the Earth. Human beings are constantly generating forms of material that have never existed before in the natural history of the universe and couldn't. So the complexification and ordering process has now gone exponential. And we're part of that. We're part of the developmental process of a self-complexifying, self-ordering universe. And if you look at the graph, it's all one process. We're just an important ramp upward in that process, just as life, when it started to happen, was an important ramp upward in that process, just as the building out of the elements by fusion and their distribution was an important part of that process. It's all one process.
Thank you. This has been really fun.
Good.
I'll put links to things in the description. It was fun reading for everything, and I just before we did this, I finished reading Lee Smolens's Time Reborn. So yeah, that's really good. And then it's older. It has some things where like you don't have the science on like supermassive black holes, but it's then interesting to see how he thinks about it. So
he's in a funny position in relationship to his own theory. I think he's almost backed off on his own theory, because I think he got treated very badly when he put that theory forward. I think the string theorists really wanted to shit on him because he was giving an alternative to the anthropic principle that was very powerful, and they needed the anthropic principle because they felt it was useful to string theory, and so they felt he was a threat. And I think he was too naive to realize that was happening, so he got very badly treated, and it put him. He's a bit gun shy about being associated with his own theory at this point. Also, because I think weird people like me have embraced it and run with it, and he's afraid of being associated with people outside the field that don't have credibility, because he could damage his credibility. So I think there's a certain amount of that going on. I don't know. Like if I send him an email and I ask him a really like focused question about a specific paper I'm looking for, he'll answer me. But if I send him something saying, "Oh, I think I'm like this is really interesting. What do you think about this?" He just won't engage. Like, he only engage with the very mainstream, like when I'm behaving like a scientist, he'll answer me, and when I'm behaving like someone who's very excited by the possibility space that his theory opens up, he gets a little frightened, I think.
Hey, but that's cool. He responds to you, and you can get help.
He's great. He should get a Nobel Prize. Like, it's an unbelievable. I think he came up with the most exciting new idea, of the past few decades. And he didn't get rewarded properly for it at all. He didn't. It's a shame. He's a great guy.
Okay, thank you.
Thank you very much, Jack. Real pleasure talking to you.
Appreciate it.